Hi everyone, welcome to another video for research design and analysis. This video is the first in our series where we'll be talking about descriptive statistics, and specifically in this video we'll be talking about measures of central tendency. So as a quick reminder, right, what are statistics? Well, statistics are the numerical summaries that characterize the shape of distributions, which allows for efficient comparisons between distributions or descriptions kind of in reference to a distribution, right? We can describe a score in reference to the distribution that it comes from. And at the population level, we talk about these things as parameters, but in general, we're not actually going to be measuring the full population. We'll be taking some sample. So we can calculate a few different descriptive statistics in our sample in order to try to make inferences about the parameters in the larger population. And broadly speaking, we're going to be interested in measures of central tendency, measures of variability, and measures of skew, or how symmetrical the distribution is. Now, central tendency will generally tend to focus on the mean as our primary measure of central tendency, and for measures of variability, we'll generally focus on the standard deviation and or the variance as our primary measures of variability. Now, I don't want you to get the impression that the mean and the standard deviation / variance are the only measures out there or the most important measures, but for the type of distributions that we'll work with, they come in handy a lot. As you work with different distributions, you'll find that other descriptive statistics might be more accurate or more efficient for summarizing those distributions, and we'll talk a little bit about that. But again, our focus here is mostly going to be on the mean as our primary measure of central tendency, and the variability the variance / standard deviation as our primary measure of variability, which we're going to talk about in the next video. Okay, so central tendency. Again, we're trying to describe the center of the distribution, as the name implies, or give people the sense of some sort of typical score or observation. So the mean, which is often written as an M or an X with a little bar over the top to indicate that we're taking the mean of the X's, right, is the average value. And you're probably familiar with how to calculate this, right? So the mean of X is taken by summing all of the X's together and then dividing by the number of X's that there are, and then this will give us a measure of the typical score in the random variable X. Now, alternatively, we could calculate something like the median, which is often just written as median or sometimes med, right? This is the value of the score in the middlemost location in the distribution. So depending on how many X's I have, the median is the one that is right in the middle, right? So we're going to talk a little bit more about the properties of the mean versus the median here in a second. But finally, the last measure of kind of central tendency or typicality that I want to bring up is the mode, because it tells us about the most frequent value. If we have, the numbers 1, 2, 3, and 3, 3 is the mode because 3 occurred twice, whereas all other numbers occurred once. So it tells you how often a particular value, or what value occurred most often. But in general, the mode is pretty limited in the type of information that it can convey. So we're not going to work with it very often unless we're dealing with something like nominal data, where all we really have to go on is kind of counts, and what count was most common might actually be kind of an important thing to summarize. So let's instead think about a hypothetical problem, okay? And we're going to talk about how we can describe the distribution of scores on a mathematics test. So let's say I've got my math test. It's got 9 arithmetic questions and it's got 9 algebraic questions on it. 114 students took the test, and I'm interested in looking at how students performed on the exam. So I might want to know, how did the typical student do, and did they generally do better at the arithmetic, or did they do better at the algebra? So I can calculate different measures of central tendency to get a summary of the scores for all of these different students. So first, let's think about computing the mean of the 9 arithmetic questions. So out of my 114 hypothetical students, here's a frequency table showing you the value, right? So what score they got on those 9 questions, right? So we had 33 people get all 9 of them right. 39 people only got 8 of them right. 15 people got 7 right. 15 people got 6 right, and so on and so forth. Right, and then we're turning this frequency into just a proportion, right? So 33 was 29% of the total sample. So this column is really just the frequency divided by the number of observations that there are. And then we can also add some additional information to this frequency table to, for instance, get a sense of the cumulative frequency, shown here in ascending order, where we're just saying, okay, well, how many scores were there up until that point, right? And our first score in this order was one person who unfortunately got a 3, right? So there's only one score at that level. but then there's 3 scores at this next level, 12 scores at this next level, and of course by the time we get to kind of the maximum value on the test, we had all 114 scores. And then these other columns give you the same information, just as a proportion rather than a frequency, and in descending order rather than ascending order. And I've presented all this information just to help give you kind of a more complete picture of the data, and this will also come in handy when we're looking at things like calculating the median, which we'll do in a little bit. But I just want to give you kind of an orientation to all of the different fields of information that I'm presenting you with right there. So as you can see, this is a lot of information. It's the scores for 114 kids, and I've already tried to summarize it, but it's pretty dense. So could we come up with a single number that provides us with a better description of how students actually did on this exam? Well, I could calculate the mean here, and I could do that kind of in 2 different ways. The first is kind of the traditional way you're probably used to thinking about calculating the mean, right? So the mean of x can be done by taking the sum of all the x's divided by the number of x's that there are. So I could lay this out with 114 scores and say, okay, there's a 3, then a 4, then a 4, then there's 9 5s, then there's 15 6s, then there's 15 7s, and so on and so forth. Eventually, I would get to that there's 860 over 114, or an average score of 7.54. Now, if I already have my data in this nice frequency table, one nice shortcut we can make is we can simplify this by actually just taking the sum of the observations multiplied by the number of observations that there are. So for instance, for the 3s, we only had 1, right, up in the table up here, so I can do 1 times 3. For the 2s, there were 4, so I can do 2 times 4. Right, for the 5s, there were 9, so I can do 9 times 5, and so on and so forth until I get to the 33 9s that I had on the exam. So doing the sum of n times x for each level of x, and then dividing by n is a handy shortcut if we've already got our data in this frequency table. If you don't have your data like this, it's probably going to be easier just to calculate the mean this way, or realistically just using a function on the computer to get the mean for you. But you can see that whichever way we take, we end up at 7.54 as the mean of these 9 arithmetic questions. Okay. Let's do the same thing, but for the 9 algebra questions. So again, all of the values in our frequency table here are the same, but briefly, let's just look at the different values and how they're distributed. So no one got a 1, no one got a 2. We had 4 people get a 3. We had 23 people get a 4, 36 people get a 5, and 33 people get a 6. Right, so just looking at these 2 columns here, we should already be getting a sense that the algebra questions were a little bit harder. Lower scores were much more common on these questions, right? Whereas before we were getting 33 people who got a 9 on the arithmetic questions, now we only have 2 people who got all of the algebra questions correct. So if we wanted to calculate the mean of these algebra questions, again, we could do that in 2 different ways. We could take the mean of x, in which we take the sum of all the x's divided by the number of x's that there are, right? Adding up all 114 of them, we end up with 619 divided by 114. That leaves us with 5.43. Alternatively, since we have this tabular format for our data, we could take a little shortcut and take the sum of each level of x times the number of observations at that level. We still end up with 619 over 114 because mathematically these 2 operations are the same, right? And we finish with a mean of 5.43. So it looks like, right, the mean kind of quickly tells us as a single number that the arithmetic questions were easier than the algebra questions because the mean on our arithmetic questions was a 7.54, whereas the mean on our algebra questions was a 5.43. So presenting people with that single number already conveys some sense that the algebra questions were harder than the arithmetic questions. Now, a lot of information is lost, right, when we boil the data down to that single number, but it is pretty quick and easy as a way of understanding how people scored. Similarly, we can do a calculation for the median. Now, again, the median is going to be a lot harder to calculate if you actually have all your data just arranged in a single column. But if we have it in this frequency table, it's a little bit easier to find, right? And again, realistically, we would probably just ask a computer to do this for us, but someone has to program that computer, so it's important that we know how it works, right? And the location of the median then is going to be the number of observations that there are plus 1 divided by 2. So 57.5 So we could come over here to our ascending cumulative frequency, right? And we'd be looking for the 57.5th observation, right? The 57.5 observation, which happens to be in the level of the value 8, right? So we had 42 observations at the end of all the 7s. Okay, so starting at 8, we have our 43rd observation, and at the end of 8, we have the 81st observation. So the 57th observation has to be in there, as does the 58th, right? So we know then that the median score for the arithmetic questions is an 8. Similarly, we can apply this logic to find the median of the 9 algebra questions. So for the 9 algebra questions, again, we solve this in the same way because we have the same amount of data. We have 114 scores plus 1. Divide that by 2, we end up with 57.5. Now we'll have to come to our cumulative frequency column here. Okay, we see that for the 4s, that takes us up to the 27th observation. And then at the start of the 5s, that would have been our 28th observation. And the 5s end with the 63rd observation. So the 57.5 observation has to be in the 5s, right? So the median score here is a 5. So the median agrees with the mean in a qualitative sense, right? Where they're both telling us arithmetic questions were easier, right, than the algebra questions. But you'll notice that the mean and the median are distinct and different numbers, reflecting their different methods of calculation. So why would we be interested in having these two different numbers as kind of different methods for ascertaining the typical score in these distributions? So here I'm plotting frequency histograms for the arithmetic and the algebra questions. And you can see again that our mean was 7.54 here, the median was 8. The mean was 5.43 here, whereas the median was 5. So they both tell us that algebra was generally harder because students are scoring worse, but clearly there's some discrepancy in these numbers. And so now let's talk a little bit about the different properties of the mean and the median so that we can better understand what each of them is capturing. So think about this for a second. If the median is the most central point in the distribution, right? It's the middlemost score of all of our scores. What is the mean? Like, how would you describe it? If the median is kind of cutting our scores, our number of scores in half, what is the mean doing? And to give you a little bit of a hint, right, we can say that the median cuts the data in half so that there are the same number of scores above the median as below the median. The mean cuts the data into something else. It doesn't put the same number of scores above as below. So how is it cutting up the data? Think about it for a second and pause the video. And when you think you have an answer, go ahead and start it up again. Okay, so the answer to this question is that the mean creates a symmetrical distribution of errors, which is to say that it puts the same magnitude of scores above the mean as there is below the mean. So the median puts an equal number of scores above it as below it, but the mean puts an equal mass of scores above it as below it. And this gives the mean some unique properties. So because, again, the mean divides the mass of scores into equal parts, so half of the mass is above the mean, and half of the mass is below the mean, that means it has a special property of making the sum of errors equal to 0, where we can consider errors as deviations away from the mean. Right? So if we're using this value to describe or summarize a set of numbers, how poorly it summarizes those numbers is going to be represented by these errors. For some of these observations, the mean is a good representation. For some of these observations, the mean is a bad representation, right? But we have a unique property here that if we calculate all these errors by taking the difference between each score and the mean, if we added all of these errors together, there'd be an equal mass of positive errors and an equal mass of negative errors. So the sum of errors around the mean would be equal to 0. And keep them, kind of put a pin in that mentally, because we're going to come back to that in future videos, because this is going to be really important when it comes to how we judge how well we're describing our data and describing particular distributions. All right, so let's take a second to refresh ourselves on some desirable properties of sample statistics. We've talked a little bit about this before, but I want to go through it again. Right, so remember, we want our statistics to be unbiased, meaning that on average, we want the sample statistic to be equal to the parameter in the population that it's estimating. Now, both the mean and the median are going to be unbiased. We also want them to, though, to be efficient, which means that a more efficient statistic is one that varies less from sample to sample. So on average, it's going to be closer to the population parameter in any given sample. And in general, the mean is more efficient in that respect than the median. So that's one reason why we're going to prefer the mean. And then we also want these estimators to be consistent. So a consistent statistic is one where the efficiency increases as the sample size increases. And you'll understand this a bit better when we talk about like the central limit theorem in some future videos. But the idea being that, efficiency is kind of how close is it to the population parameter from one sample to the next. Consistency means if I take a bigger sample, can I get even more efficient? And we find that both the mean and the median are consistent. So one reason why we're generally going to prefer the mean over the median is for its efficiency, but it's also important to understand some of the properties of these statistics as we calculate them, what they're sensitive to, right? Because that can be, and what they're sensitive to, because that can be kind of a double-edged sword. If you're sensitive to something, that means you'll detect it, but it also means you can be pulled and swayed by it. So we want to think about the mean and the median in a little more detail. Again, both of these measures of central tendency are based on the notion of balance. The mean is sensitive to each data point or datum's distance from the middle, right? You can think about this if we have our distribution of scores here. So we're looking at height in inches, and then we have the frequency of students at each height. In this perfectly symmetrical distribution, the mean and the median are going to be in exactly the same place. However, if I take some of those data and I actually move them over a little bit, now the mean is going to move. The median is not, right? Because as long as those data that I move don't cross over and go into the bottom half of the distribution, the median is still the middlemost score. But the mean, right, is trying to keep an equal mass of scores above as below it. So it's sensitive to every data point in this distribution. And if we make some of those data points more extreme, the mean is also going to become more extreme. So in some circumstances, this can be a desirable property of the mean, but it can also be a problem because it means if you have one outlier in your data set, your mean is going to get pulled in that direction. This makes the median actually a lot better and more desirable for kind of irregular and skewed distributions. So if you think about, for instance, something like household income, where most individuals have a more modest income and then you have a few individuals with an extreme income, the mean might actually be a bad description here because it's going to be pulled way up by these outliers and make it seem like the typical house is actually richer than it is, right? So here's our mean. In this case, it actually works out to be about $63,000, but the median household income is about $46,000, right? So the median actually tells a better story here because it's a better representation of the typical household, whereas the mean is getting strongly pulled by these outliers in this tail, making the typical household seem like they're doing a lot better than they really are. Right? So depending on your distribution, using the mean or using the median might be the better choice, even though the mean is generally a more efficient estimator. So we can see this sensitivity, right, in terms of the effect of outliers a little more clearly in this illustration. So here we're looking at a working memory task in a psychology experiment where we're looking at the number of digits that individuals can kind of successfully recall over a short period of time. And you can see for most people, right, it's under 10. It's in a pretty modest range. But for one person, they had an extreme working memory and they had the ability to recall 40 digits in a row accurately. So that's pretty unusual. Now, if we calculate the mean with that outlier in there, right, that's going to bump up what we actually estimate as the typical performance for a person, right? If we exclude that value, now the typical performance for a person drops down. So the mean is going to be sensitive to those outliers. So we have to think carefully about whether or not we want to use the mean in a situation where we have outliers, because its sensitivity to every data point, which is a desirable property, means it can be swayed by outliers, which is an undesirable property. So finally, let's talk a little bit about the mode, right? Again, the mode tells us something about the most common value. So all it is sensitive to is the peak in the distribution for continuous variables. So for these data, right, we would say, well, the modal height was 64. But the downside of the mode is that it's pretty simple and insensitive. So we don't know, if you tell me that the mode was 64, did the data look like this, right, or like this? And the mode doesn't really tell us much about anything else going on in the distribution because it is so simple and insensitive. It works for some things, but by and large, the mode is not a descriptive statistic that we're going to use very often because it doesn't really tell us a lot about the distribution we're trying to describe.